Spencer talked about earlier Nick Shackleton. I wanted to mention him briefly. One of the great things about PowerPoint, you can throw in things right at the last minute. Nick wasn't so much a mentor of mine, more than a role model. But I remember being at a conference about 15 years ago, and he was also well known as a clarinetist. And I could hear him play, and I walked up to him and I asked him for advice, and he said, there was one thing that he told me that I should always remember in my career, and that was to give myself time to think. And I think when I see some of my junior colleagues at Harvard and at the other institutions I've been involved in, they're running around like crazy, publishing, reviewing, etc. They just never seem to give themselves time to mull over a few of these problems. I've been at Harvard a couple of years. I was hired there in some sense because I sit smack dab between solid earth geophysics and climate research. So because of my sort of interdisciplinary background, I guess. And that's a connection, that's a bridge that hasn't really been completely mined yet. There's so many interesting problems at that interface, but there's only a handful of people that are working at that interface, and with students coming up, I think it's nice to see that that's changing. My niece is a political scientist in London, and when I moved to Harvard, she called me and said, so what's it like being at that really august institution? So I thought about it for a while, and then I sent her a picture I took from the parking lot next to a Chinese restaurant in Cambridge, Massachusetts. I live right near it, which I thought summed it up pretty well. This is a very Harvard-y type sign to see. We all walk around with dictionaries and things. Okay, so I'm going to set the stage here today by talking to you about what we certainly know, without any doubt, about 20th century global sea level rise. Is there any chance somebody might get me some water? I forgot to. I can take that. This is something that is universally accepted. If we're thinking about 20th century sea level rise, we take a look at tide gauge records. These are tide gauge installations distributed around the world. They've been collecting data for, in some cases, hundreds of years. They're very low-tech devices. They're just cylinders with a float or a ping pong ball inside, and as the water levels go up and down, they float up and down, and all you have to do is monitor their level, and in many cases, you get very nice, very pristine measures of sea level rise over decades to centuries. So what do these tide gauges tell us? Thank you. I'm on decongestant, so I'm all dry. Okay, well, spilled on my laptop. That's not going to be good. Oh, actually, it's not my laptop, so that's even better. Okay, well, there's a worldwide distribution of tide gauges, several thousand of them, both in the north and southern hemisphere, although most of them are in the northern hemisphere. If you take a look at the global average sea level that you get out of these tide gauges, you get a trend that is an inexorable rise. There's very few years in which the sea level is falling. And if you take a simple rate of that, you get probably 2.3 millimeters per year, so about an inch every decade. Depending on which analysis you look at, what selection of tide gauges are used, you get anywhere from 1.5 to 2.5 millimeters per year of sea level rise. Okay, there's no doubt about this. This is universally accepted. Anyone who does serious sea level research would not dispute this for a second. Okay? But if you give talks like I do, public talks, and if you get emails like I do, somebody alluded to the emails that we all get when we work in climate research, those emails and those public talks are often, three statements often arise from what I call the skeptics of sea level research and the connection between sea level research and climate change. The first is that, well, 2 millimeters per year is simply not anomalous. Sea level's been rising at this rate for thousands of years. That's one of the most common things that I hear. The second is that, well, and this is a significant problem in some senses, that sea level change is not constant around the world. It varies dramatically from place to place. And that seems to be an argument against melting of ice sheets because those should raise sea level more or less uniformly, or that's how the logic goes. And then the third statement we hear is that, well, 2 millimeters per year is stable. It's not going to change. There's nothing to worry about. So what I'll show you in this brief talk is that these three statements are indisputably false, right? But a more interesting aspect of it, particularly for this audience, is that in considering these statements, even implicitly, like many of us do in sea level research, it's provided us with a lot of insight. So you engage your skeptics, right? The last speaker was talking about conflict, and I was reminded of an F. Scott Fitzgerald quote where he said, conflict has a value beyond victory or defeat. And in this field, the value is deeper insight, which allows you to move further into the future, project more accurately. And I'll try to explain why that is. Okay, let's start with this one. 2 millimeters per year is not anomalous. It's been doing this for thousands of years. This is by far the easiest of these statements to repudiate. I was born in Australia, Melbourne actually, down here. If you look through the equatorial Pacific, these features are endemic. The quaternary scientists call them 3-meter beaches or 3-meter corals. This is a dead coral. There's a live coral under here. It's 3 meters. The top of this coral is 3 meters above sea level, 10 feet, and it's been aged, as many of these features are, about 5,000 years of age. So just think about it. These are endemic. Every one of these islands that you see listed here has features like this. If sea level was rising at 2 millimeters per year for the last 5,000 years, this coral would be under 10 meters of water, and it isn't. So a very simple repudiation is to say, wait a minute, that's simply not true. But let me give you some more subtle data sets that have come online that show this in an even more beautiful way. And I'll start talking about archaeological evidence. The first is from a paper by a colleague of mine, Kurt Lambeck. I don't actually work directly with Kurt, but we talk quite a bit. He analyzed fish tanks. Wealthy Romans about 2,000 years ago owned fish holding tanks. People went out, they fished. The fish were then placed in these holding tanks, so when the Romans had their meals, they could just be they could eat fresh fish anytime they chose. This was kind of the height of ostentation in the Roman Empire. I guess the decline came soon after, right? Well, these fish tanks or piscina, here are some examples of them, and this is Kurt Lambeck standing on one. These don't have a lot of archaeological significance, at least according to typical archaeological thought, so they're unprotected. I've swum out beside many of them. There's a whole suite of them along the Roman coast here, or the Italian coast here. And the nice thing about them is that when they were built at a very precise level relative to high tide. I'm giving you examples of them. The last picture was examples looking from above. This is now going into the water, and you see this engineering. You basically have the fish in this area. There's 2 columns of concrete, another column across here, and a sluice gate which had holes in it. As water went up and down with the tides, these fish tanks were refreshed, okay, each time they were. But that fish tank was set up so that the top of this sluice gate was, in current terminology, 20 centimeters above high tide, okay? And of course, that's important because if you place them too low, the fish would simply get out at high tide. The nice thing about that is that we can look at a whole bunch of these fish tanks, and we can measure their current elevation relative to high tide. We understand how tides have changed here, and we get a very accurate estimate of how sea level has changed in the last couple of thousands of years since these fish tanks were built. And when we do that, we see that sea level has risen in this last few thousand years by about 1 meter. Okay, that's 0.5 millimeter per year. But there's a caveat here, and that is I'm also an ice age sea level modeler. I look at sea level change through the ice age, and I can predict rather accurately how the ice age would have affected the sort of ongoing effects of the ice age that ended 5,000 years had affected these tanks. And when I do that, when I correct for these ice age effects, I'm left with nothing at all. So according to this fish tank data, sea level change has not occurred over the last 2,000 years. And remember, if sea level was going up at 2 or 2.5 millimeters per year, sea level as it was in the 20th century, then these fish tanks would be 5 meters below present sea level, and they're simply not. I'll give you a third data set, and I'm including it because I've been involved in the analysis of it. One of these really beautiful data sets, a Herculean compilation by Stevenson and Morrison about a decade ago. They looked at ancient eclipse records, which told of when, of course, these ancient cultures, the Babylonian, the Chinese, etc., weren't really astrophysicists or astronomers. They were more astrologers. Eclipses were harbingers of bad tidings, right? They took a look, these guys took a look at the data set of ancient eclipses, and they plotted this as a function of time. I'll try to explain. This is a function of time. We're out here somewhere. This is 2,500 years ago. And what this axis is, that's the time that that eclipse would have occurred if the Earth's rotation rate had stayed constant and equal to today's rotation rate, right? Relative to the time where it actually occurred according to those records. And what it shows is this very systematic trend downwards, which simply means that the Earth's rotation rate is slowing down. And we know the Earth's rotation rate is slowing down. There's a very simple explanation for that. That's because water waves breaking on shorelines, and sometimes even in the deep ocean on shelves, causes a dissipation which acts to slow the Earth's rotation rate. And we have very accurate measures of how that slowing is occurring. And there's a step, a sequence of steps that gets to that measurement. If the Earth's rotation rate is slowing, the Moon is orbiting the Earth faster. If it's orbiting faster, it's moving away from the Earth. And we know how fast the Moon is receding from the Earth because the Apollo astronauts were nice enough to put up mirrors there, and we can measure two-way travel times back and forth. But the important thing is, if we take into account this tidal dissipation effect that we know very accurately, then the slowing of the Earth's rotation matches the observed slowing when you compare ancient eclipses with your predictions based on the current rotation rate. Why is that important? Because if ice sheets were melting for the last 2,000 years, you would be taking mass from the poles, putting it into the equator. You'd be slowing the Earth down. You'd add an additional contribution to this slowing if you were melting ice sheets, a sizable contribution. It's in fact that. If I take this curve, which is tidal dissipation plus some ice age corrections, I add the slowing that would have occurred if we were melting polar ice sheets for the last 2,000 years, you grossly misfit the data. There is simply no way in which that could have been occurring. So that's the first one, and in fact, it's the easiest one to dismiss. 2 millimeters per year of sea level rise in the 20th century was anomalous. We had seen nothing like it for the last 10,000 years until we were in the midst of the Ice Age. Let's look at this one, which is probably the most counterintuitive research that I've done in my career. The observation is if you go all over the world, sea level is rising, some places it's falling, it's varying geographically in a very dramatic way, therefore ice sheets cannot be the culprit. So to convince you of the fallacy in that argument, I'm just going to take a very select group of tide gauge records compiled by a guy named Bruce Douglas. He's very careful in looking at sites away from cities. You don't want to look at tide gauges near cities where groundwater pumping is altering, is causing the cities to subside. You don't want to have tide gauges near places where one plate is descending under another. And you need more than 10 or 20 or 30 years of data. One of the speakers talked about this. There are strong decadal fluctuations in this data. To get a 20th century trend, you need tide gauges which have at least 30 years of data. And he came up with this compilation. And now I'm going to show you, this is the sea level rate in millimeters per year at these 24 tide gauges that are thought to be the really important gold standard tide gauges in this research. In most of my research, I used hundreds of tide gauges, but I was forced to use these by reviewers. So let's look at these. These aren't grouped in any significant way. These are European tide gauges, New Zealand, US West Coast, South America, US East Coast. So I've just put them together. And then you take the average and you publish your paper. In this case, the average was about 1.5 millimeters per year. You notice a trend that's been noticed for decades, which is that European tide gauges indicate that sea level in Europe was rising at lower than the global average over the 20th century. That's, no matter what selection of tide gauge data you use, you see the same observation. And in fact, that's given a name in the literature. This is called the European problem, right? So nobody had a clue what was causing that. I'm happy to see that my spill is drying underneath here. Okay. By taking the average, you're assuming something, and you're assuming it implicitly. You're assuming what we call the bathtub model. If an ice sheet melts, so here's an ice sheet, it melts back down. Here's old sea level, here's new sea level. You're assuming that sea level will rise uniformly if an ice sheet melts. That isn't even close to being true. In fact, an ice sheet, let's look on the right here, has mass. It exerts a gravitational attraction on the water near it. So water is gravitationally attracted to the ice sheet. If the ice sheet melts, two things happen. You certainly dump water into the ocean. There's no doubt about that. But the second thing you do is that you relax this gravitational tide. You relax the pull on the water. And it turns out that near an ice sheet, that second effect wins. If I'm standing at the edge of the Greenland ice sheet and it catastrophically collapsed, sea level at my feet would drop 100 meters. Highly counterintuitive, but not in any sense controversial. This is just Newton sitting under the apple tree. There's nothing, so many things that I do are theoretical or involve a sequence of parameters that each require some justification. This is just Newton's law of gravitation, right? So let's look at what the implications of this are. This is a numerical simulation where what we've done is we've melted enough from the Greenland ice sheet to raise global sea level 1 meter on average. If we added it all up, divided it by the area of the ocean, we'd get 1 meter. This is what actually happens to sea level. The blue here is the zone around Greenland where sea level falls. And what I didn't tell you when I saw this plot is that hinge point, how close is that hinge point to the ice sheet? Where do you go from sea level fall to sea level rise? It isn't near the ice sheet, actually. It's 2,000 kilometers away, which is roughly this distance in blue. So, if Greenland melted catastrophically tomorrow, and you happen to have a friend, I was giving a talk recently, and I made the terrible mistake of calling Scotland the northern tip of England, which I'll never do again. But if you have a friend in Scotland, they may be justifiably concerned, but they shouldn't be, except in some broad humanitarian sense, because sea level would fall in Scotland if the Greenland ice sheet melted. It would also fall in Newfoundland, etc., but you pay the price somewhere, and as you move further and further and further away from the Greenland ice sheet, you get more and more sea level rise. This is a 30% increase in sea level relative to this 1 meter that you predicted. But there's like a delta function, a very steep dip near the ice sheet, so that in this simulation, where we melted enough to raise sea levels 1 meter on a globally average sense, sea level would fall in Greenland by about 25 meters. That is a very significant sea level fall. And the important thing is that these effects aren't just, I sort of cheated in showing you this picture by just looking at gravity. There are also deformational effects. When the ice sheet melts, the crust comes up, and that's also included in these analyses. But clearly, this geometric pattern is going to be distinct for each ice reservoir that might be melting. And that's why these patterns have come to be known as sea level fingerprints. The idea now is to look at fingerprints for all sorts of melting scenarios. This is the Greenland one I talked about. Antarctic will have its own fingerprint, where you have this zone of sea level fall nearest to the Antarctic. And glacier melting systems like Alaska, Patagonia, etc., will have their own zones of sea level fall around them. So now the question is turned on its head. At first we were told that if sea level varied geographically from place to place, it could not be because of ice sheets melting. In fact, it has to be, in some sense. If ice sheets are melting, the sea level change has to be geographically variable. And that variability tells you something really important. Now we can go beyond just saying sea level is rising in a globally average sense of value of so-and-so. You can actually, by looking at that geographic variation, tell where that meltwater is coming from. You can add these fingerprints up in a sort of least squares approach, and you can actually determine, with a few very good measurements of sea level change, you're sitting there in the ocean, it all looks like water to you, but by looking at the geographic variation of that change, you can actually infer which of the reservoirs were contributing how much. And to give you an idea, this isn't a unique solution. I don't know but this is just one particular solution where we added up sea level, added up sort of a weighted amount of melting from the Antarctic, Greenland, and mountain glaciers. And you can see that you can now capture that geographic variability very well. It's a very powerful way to do a sea level analysis now that's only really come to the fore in the last 3 or 4 years. When people are looking at satellite data, I'll talk about that later, or this more low-tech tide gauge data, the action today is in trying to extract fingerprints and in understanding the source of the meltwater. Now, even with a very simple physics lecture that I've given you, we know how to solve the European problem, right? If Europe shows less sea level rise than the global average, what possible cause could there be? Well, Greenland must have melted, because Greenland is closer to Europe than it is, or Europe is closer to Greenland than the global average. And by melting from Greenland, you don't get the full effect in Europe of the sea level rise. You're still in this zone where the gravity plays a role. So there's a very simple explanation for this reduction in sea level rise. And again, by answering the skeptics, it provides a very beautiful way of developing an example of developing a deeper insight into the physics of sea level change. Now here's the last one. 2 millimeters per year is small and it's stable. It won't change. The problem with this question is it already has changed, without a doubt. Here's that plot I showed you before. This is from these low-tech tide gauges that are distributed around the world, and this is the rate, 2.3 millimeters per year. But we have other ways of measuring sea level change. In fact, in the last decade and a half, most of my colleagues, I do this too, but I like tide gauges because they're longer, but look at satellite data. It's an image I just pulled off the web of the Topex Poseidon satellite. It's just by measuring two-way travel times, measuring the change in sea level as a function of time. And when you do that, you actually get a rate that is closer to 3.5 millimeters per year. So a 20th century average is 2.5. In the last decade, it's 3.5. That rate has already changed, right? So there's no going back in some sense. And there's no doubt it's going to continue to change. In fact, one of the most cautionary aspects of the IPCC report that was just published is that the present-day rate of sea level rise that are measured by the satellite Topex Poseidon-type missions is already at the upper bound of the IPCC projection. And there are some of us, myself included, who believe that that upper bound in the IPCC projection was too low, right? And I think the fact that we've now reached that upper bound is an indication of that. Okay, so what about the future? Let's go forward a little bit. We've published several papers now. We think we understand the physics of sea level a little bit better. We understand the variability. We've been able to throw out these ideas that sea level, 20th century sea level was not anomalous relative to earlier changes, and that it's in fact changing as we speak. What would happen if an ice sheet catastrophically collapsed now? Let's take the Antarctic ice sheet as an example. Professor Prin earlier had talked about it. Why are we so worried about the Antarctic ice sheet? We're worried about the West Antarctic, in fact. This region to the west, although it's hard to say what's east or west on the Antarctic, of the Transantarctic Mountains, is a region that is essentially underwater, under sea level. If the ice sheet wasn't there, it would be primarily an ocean. And because of that, there are concerns about its stability. But I'll say a few words about that. Good news, a little bit in a couple of minutes. So for a variety of reasons, we're concerned about the stability of the Antarctic ice sheet. What would happen if that ice sheet melted catastrophically in the next 200, 300, 400 years? Well, we heard a quote about the value that people cite. That's 5 meters. So the IPCC report would say about 5 meters of globally average sea level rise. But you already know from my talk that it's not going to be the same everywhere. You're going to pay a steeper price in some places than others. So let's do the same fingerprint analysis. Let's catastrophically collapse the West Antarctic ice sheet and see what happens to sea level. And if we do that, that was just my example of why we're concerned. These are pictures that you see all over the place of the shelves breaking up. The Wilkins ice shelf here and Larsen B here. This is taken from the Gore book. Another reason that we're so concerned about the West Antarctic, of course, is that there used to be, when I was a graduate student and beyond, you would go to talks that would say nothing really to worry about because, yes, the edges of the West Antarctic ice sheet will melt, but the interior will get colder, precipitation will build, even though it's a desert, and there'll be a balance between accumulation in the center and depletion at the edges, right? So that idea was thrown on its head recently in a Nature article which showed that the entire West Antarctic ice sheet is in a zone of warming, okay? There's no refuge from the warming, it seems. Well, here's what will happen if you catastrophically collapse the West Antarctic ice sheet, okay? This is at 5 meters I talked about. That would be the average sea level rise that you'd get. If you took these colors and just took an average over the ocean, you'd get 5, right? But because of a series of effects, gravitational that I've talked about, but there are 2 other effects that I haven't talked about. One is that people used to think that if the West Antarctic ice sheet melted, you'd be left with this hole. And that's great because that would be a repository for water would just stay in this hole. It wouldn't get out into the wider ocean. One of the problems with that argument is if the West Antarctic ice sheet melted, that hole would rebound upwards. And that rebound throws water out into the ocean. That's an effect that had not been included. There's an even more subtle effect. If the West Antarctic ice sheet melted, the Earth's rotation pole would be perturbed. It would actually move 0.5 kilometers away from its current location. And that acts also to throw sea level, make sea level even more geographically variable than you think. Unfortunately for us, the worst place to be is on the coast of the United States, okay? That's where the peak is. That's where these 3 things, rotation, this rebound, and this gravitational effect that I've talked about, you get a triple whammy here. In fact, somewhat ironically, off the east coast of the United States, the maximum sea level rise is just off where we are here, Washington, D.C., and along the west coast, of course. This was published in Science about a year and a bit ago. You also get whammied in the southern Indian Ocean. There is a piece of good news here, though, right? This is a graduate student of mine, Natalia Gomez, who's published extensively on this, and she's just published a paper which is, I think, it was sort of interesting. Let me give a sort of comment. She came into my office once and she showed me some results. And, you know, she's a young graduate student. She's writing these high-profile papers on sea level, showing what will happen to the U.S. East Coast. And then she saw something that was quite interesting. She came in and she said, "What do we do?" And I said, "Well, we publish it." And what she had shown is that this sea level fall helps you. Because remember, this is a marine-based ice sheet. The old idea was, as you melt ice sheets, sea level will rise, thus further destabilizing the ice sheet. But if the West Antarctic ice sheet melts, sea level will fall at its grounding line, and it will act to stabilize the ice sheet. There is a self-stabilization that has not been included in previous analyses. That's the good news. That sea level drop will actually help you a little bit, right? And she has several papers now in press on this idea. But let me end with another overhead that I showed. Professor Prin earlier had talked about the Eemian, right? Stage 5e, 125,000 years ago. This is a time where, as he said, where there's a lot of effort these days. We want to understand what sea level was like during these interglacials. We're in an interglacial. The last one was 125,000 years ago, which was the basis of this work. And there's others, roughly 100,000 years in the past, okay? We're interested in that because 125,000 years ago, the average temperatures were roughly the same as the temperatures that we're going to experience in the latter part of this century. So that provides a very interesting natural laboratory. The last time we had temperatures that are equivalent to where we're headed, what happened with the polar ice sheets? What were they like? What was sea level? And as we heard in that first talk, the typical average that's quoted is 4 to 6 meters. Sea level was 4 to 6 meters higher 125,000 years ago than it is today. That's been true for 10, 15 years. That's the quote you hear over and over, okay? The problem with that is that it doesn't take into account the fact that when you're looking at data, you're sort of sampling with very few data points a field that is highly geographically variable. So the question is, when you take into account the sea level physics and you actually look where you have data and you redo the analysis, what happens? Well, that 4 to 6 becomes 6.5 to 8. No doubt about it. And this was where we, in a Nature paper about a year ago, where we used IPCC terminology. There's a 95% probability that global sea level at the last interglacial peaked 6.5 meters higher than today. So a 95% probability that sea level rose higher than what was your upper bound until you do the sea level analysis, 4 to 6 meters. And you have 67% confidence that it would reach 8 meters. And there is no doubt that in that range, you had sizable collapse of both the West Antarctic ice sheet and Greenland. There can be no escaping that conclusion now. Those ice sheets had largely disappeared at the last interglacial, or at least marine-based sectors of the West Antarctic and a sizable section of the Greenland ice sheet. So this is just as a summary. As I said, for those of us who work at the interface between solid Earth geophysics, which is required to do these kinds of studies, and climate, sea level is a natural place to be active. As we've worked on these sorts of things, I've been active in it for 15 years now or so. My early interest was in sea level over hundreds of millions of year timescales, right? We always face these three things. Either that it wasn't anomalous relative to what had happened before in the 20th century, that it hasn't gotten any worse, and that this geographic variability was somehow an argument against ice melting. As I hope I've shown you, all three of these things are false, and more importantly, they forced us, by addressing these issues, they forced us to look at sea level with a sort of renewed interest and insight that will help us go into the future. So thank you very much.